have one of our visiting scholars from the Oregon Transportation Research and Education program, Dr. David Noyce from the University of Wisconsin. And he's going to talk to us today about traffic safety engineering at Wisconsin using traditional methods with full-scale driving simulation to advance roadway safety. So with that, I'm going to turn it over to David. Welcome.
Thank you. Good afternoon, everybody. Nice to see you all. As Chris pointed out, I made the trek out here from Madison, Wisconsin, and I'm not sure how many of you have had a chance to visit Madison before, but we're a much different city than Portland, especially when we talk about transportation, in the sense that our central part of the city is a 1-mile isthmus through downtown. So we have water, but our water constrains the city. So the transportation problems become much different than what we have in a city like Portland. The university campus is very spread out, waterfront, very nice. Welcome all of you to come visit at some moment in time and let me know. And of course we have our main halls, and our students tend to really enjoy the waterfront on probably more nights than they should, but nevertheless that they do enjoy some of those activities as well. But back to the discussion for today. Well, what I thought I would do is to hopefully not get too focused on any one topic, but to give you a bit of an overview of some of the things that we're doing at the University of Wisconsin, but add a theme to it. And what hopefully you'll see as we go through the process here is that I think safety needs to change, especially when we talk about safety-related engineering. And I'm going to tell you about some of my thoughts as we go along here. So we'll look at some of what I call the traditional and common approaches, and then some of the new methodologies. And by all means, this is a discussion. I know it's a little bit different when you have the cameras and other things on here, but if you have questions or have anything you'd like to add or suggest as we go along, by all means, please do. Okay, let's get started. Before we start any discussion about traffic safety, especially in the academic world, we always have to make sure we're talking about, or at least we're all talking about the same thing. So I asked the question, what is traffic safety? And it may mean different things to different people. A simple definition like this isn't always as simple as you may think, right? So to avoid a lot of words, we can frame it in a number of different ways. So we can talk about it as some sort of freedom from danger. We can talk about it in terms of minimizing risk, or you'll often see the literature talk about safety being the reciprocal of risk. But we almost always relate it to crashes. Would you all agree with that? Right? So when you think about safety, we think, well, the most unsafe places are the ones that have the greatest number of crashes, and then opposite for our safest areas. But we have to ask ourselves this question. So is a roadway with no crash history necessarily safe? And I think we would all answer that question, or we probably all know locations, right, that are substandard in curve, substandard in sight distance, that we know that there is a safety issue there, but because drivers have changed their behavior to some degree to accommodate those substandard conditions, we tend not to worry about these as much as the other high crash related locations. So I think we keep this in the back of your mind, and we'll come back and visit this a little bit and see what you think about dealing with these types of situations. The other, and I'll use the word traditional quite a bit as we go through our discussion today. And what I'm trying to frame is the traditional ways, the common ways we have for looking at transportation safety-related issues. And we're all familiar with NHTSA and their safety facts that come out on an annual basis. And if Oregon is like Wisconsin and a lot of the other states I'm familiar with, we often take rates either at the fatality level or at just a general crash level and look at these rates on average compared to our roadways, right? And if our roadways are below that average, we think we're probably okay. But in those locations where they're above that average, then we believe there's some safety improvements that need to take place. And we focus on those rate-related issues. So let me move now into some more specific elements of safety and some things that we're working on, and see if I can help continue to frame the picture that I'm hoping you will see when we get to the end here. We spent an awful lot of time over the last few years in Wisconsin looking at issues related to cross-median crashes. And there's a lot of words on this slide, I realize that. But I wanted to make sure we were all talking about the same thing, or at least thinking about the same thing as I discuss this topic. And we've looked at it a couple of different ways. Obviously, we're talking about divided roadways. So most often our highway or our freeway systems that have the grassy medians. And we've looked at it in a couple of different ways. One is clearly when someone goes from a northbound direction, crosses the median, and impacts the vehicle in the southbound direction. That's the classic cross-median crash. But there are certainly many situations where someone goes through the median and fortunately finds a gap in that opposing traffic, or the opposing traffic is light and does not impact the vehicle, and nevertheless doesn't always show up in a crash report, but very much similar, as well as the attributes often that cause, or the initial cause of that crash, are the same. So we wanted to look at both of those to some degree. Now that's not the best picture in the world. It's taken out of a window of a vehicle, but as you can see here, and I think I have a laser, I mean the impact of cross-median crashes are generally quite significant, right? I mean, so this was a fatal crash, and you see a lot of the debris, and there's, for obvious reasons, because of the speeds and sometimes very narrow medians, it becomes a very important safety topic we need to take a look at. Now, like most states, and I noticed when I went down to visit Oregon State yesterday, so I went down to Corvallis, and I noticed along I-5, a lot of median barrier, a lot of both concrete and cable guard, and I think I'm right on that, Ed. So, and that's what most people have done, right? So most states have done is looking at ways to protect that median, prevent some of those crossover crashes from happening. And we know that, for the most part, even with some heavy vehicles, that they tend to work pretty well. But the question Wisconsin was facing is they were not a state that had implemented a lot of median barriers. And the question was, how do we do that? What are the warrants? What are the criteria? What are the safety-related benefits and costs of implementing a barrier system such as these? So where we went was to AASHTO, and AASHTO had developed a warrant-based system based on average daily traffic and some element of median width. There was an area that says, well, if you have these conditions, some form of median barrier may be warranted. And Wisconsin had thought about it some years past, and although approximately the same, the red line represented what Wisconsin thought was a warranted area. And then we searched around like you always do when you start research, and looked at what are some of the leading states doing, and California was one that actually began to quantify this issue a little bit more in a more focused way in terms of, their warrants were if you have more than a half a cross-median crash per mile per year over some extended period of time, then median barriers should be warranted, and then a smaller rate if you have fatal-related crashes. So taking all this information, we said, well, how should we deal with this in Wisconsin? In fact, it even went farther than Wisconsin in some of the thoughts through the Midwestern states. Those of you who have been involved in this type of research know it can be, or I should say, it's very labor intensive, right? And especially when you have a crash database that doesn't include this crash type. So what my wonderful group of graduate students did was go hand by hand through 37,000 crash reports. That took some time, right? And they still like me to this day. I believe they do anyways. At least they'll tell you that publicly. But nevertheless, we went through all these crash reports. And after filtering through, and just the reason why we had to go through so many, because we knew that there was some median element in this crash report, but until you actually got into the narrative and the description that the police officer put in the report, we weren't exactly sure if indeed it was a true crossover type crash. So we had to make sure we were dealing with the right type of crash. And once we narrowed it all down, that 37 turned into about 1,500, and then we were able to make some decisions about the types of things that we were looking for. And if you look at the state of Wisconsin, and our freeway systems are very much illuminated by the dots on these maps, right? So as you might imagine, our major freeway systems, our interstate systems, our divided highway systems were frankly littered with median crossover crashes at different locations that obviously the scale of the dots make it look a little bit more continuous than what it really was. But nevertheless, when we look at multiple vehicle crashes, quite a number of them, and then when we look at single vehicle crashes, kind of the same type of issue. Okay? So the core thing, and kind of staying within the theme, if you will, and not getting into too much detail here, but what you notice is there's an awful lot of dots that are outside of this so-called warranted area that AASHTO and Wisconsin had had tried to identify. So the key problem was, why was these median crossover crashes happening, especially in median widths of 100, 120, 140 feet, and how to warrant improvements in the safety system that can address some of these particular issues. What you also notice, and probably to no surprise, is that when we look at both the single vehicle and the multi-vehicle crashes of median crossovers, as ADT goes up, the distribution between these two change, right? So as ADT goes up, the logic would tell us that there's less gaps, so the likelihood of finding a gap in that opposing traffic changes, right? And that's exactly what we saw. So that data was all consistent. So our goal was to develop some sort of predictive warrant. So beyond the traditional warrants, can we develop a predictive warrant that says, well, based on what we know, we anticipate there to be a safety problem here in the future, and therefore we can address it before we wait for the crashes to happen. And we looked at a number of different barrier types. We compared it against other median barriers, and kind of went along again, the traditional methodologies of safety research. We also got into looking at every element of our roadway system in Wisconsin, and we have a photo log system that perhaps you also have here in this state. And our creative graduate students developed a little data collection system online and in some software elements, so we could drive the photos and identify a number of what we thought were going to be the key variables in this analysis in terms of how many of them are there and the locations that they exist. So once we got to the end here, there's way too many numbers up here for you to process, but we began to go through the statistical procedures of identifying what are those key variables that exist in predicting these types of crashes. Okay? And if I can summarize this into some words, this is what we know. We know that some logical, some perhaps not so logical, but there was a number of factors that increased these types of crashes. ADT would change it, so I think we all probably would expect that along with median width. But the common areas were near bridges and the entrance and exit ramps that go along with it. So the merging conditions, people coming on and forcing vehicles off in a crossover type application. Left curves tend to lower the number of crashes, and that makes some sense, right? So if you're going to go off the road, you're not going across the median. And we were able to develop some benefit cost type models that they're able to use to predict these types of crashes. Okay? So that's a very traditional way of looking at a transportation safety problem. So now I'm going to switch topics. I'm going to talk to you a little bit about roundabouts. This pumpkin was carved by one of my graduate students for Halloween. And after I realized and got a copy of this photo, I sent him to Student Health Services because I think he's starting to lose his mind. When you start doing transportation stuff like this, graduate school might be getting to you a little bit. So we had him checked out, but the best I can tell, he's all okay. All right, so roundabouts, they're coming everywhere, right? And a lot of states have mandated their use, or at least encourage you to consider roundabouts before you look at some more of the traditional type of intersections. I'm going to get to the safety issue in just a second here, but I wanted to start out on this topic by a bit of an operational related overview to share with you. And one of the key things that we did with this particular research was to look at a number of the different software packages that are commonly used to analyze the capacity of roundabouts. And the reason we went down this route was because the problem roundabouts that we were experiencing in our state, I believed, were due not necessarily to some sort of traditional safety-related issue, but to some perhaps the design and planning-related substandard in nature that led to a design that wasn't necessarily favorable from day one, and that led to some of the safety problems that we were experiencing. So perhaps you're familiar or you've heard of some of these software packages, and we can talk about more details on this afterwards if you're interested. But we wanted to see how these software packages performed against a known set of problem roundabouts. And we looked at roundabouts in the city of De Pere, Wisconsin. Probably doesn't mean a whole lot to you. but perhaps the city of Green Bay does. And Green Bay is or I should say De Pere is a suburb of Green Bay, so it's up in that upper pocket of the state. And so again, in a traditional type approach, what we did was look at how the existing system was operating and put in the same parameters to the software and tried to compare them. Was the software predicting what we were seeing? And as you can see, and I'll summarize it a little bit more clearly for you here in a second, in a lot of cases it was not. This graph on the right-hand side gives you some idea, and I've generalized the source of some of the software by region of the world. We were seeing quite a bit of variability, and this is a summary not necessarily of the operational results, but of the mean squared error of some of the findings. And it's quite variable. We could get some improvements when you calibrate the system, so we tried to bring them all together. It wasn't too bad. But what we ended up doing was, and let me emphasize this little point here, so that this is our opinion. This isn't necessarily something that everybody would agree with, especially the authors of the software. But what you see up here is if the circle is white, then it wasn't doing so well. The circle was black or near black, then the software seemed to be doing quite well for at least our experiences in our state. So as you can tell, again, not to necessarily promote and or not promote some types of software, you know, these bottom two, the CIDRA and HCS, tended to perform quite well and matched what we were seeing in the state of Wisconsin. The one software package that Wisconsin had mandated through the DOT for everybody to use was the top one, Rodel. Okay? And again, you know, my objective is not to pick on Rodel because there's some very nice features of that software. But what it confirmed was what I started explaining to you at the beginning of this section is that the safety problems we were experiencing may have been not necessarily due to the operations, but we were starting off with a bad model that led us to some designs that were substandard, and that led us to some of the safety issues we were experiencing. So let's talk about the safety issue then a little bit. Again, the map of the state of Wisconsin, and I won't list off all the cities for you and locations, but we looked at a number. I think there was approximately 24 or so roundabouts that we took a look at and analyzed them in great detail. And again, I'm going to overwhelm you with a bunch of numbers on a slide. And my point simply is to show you that at each one of these 24 locations, what we began by was looking at how just basic crashes were happening before at the traditional intersection and then after the roundabout was constructed in, again, what I'm calling the traditional 3-year before, 3-year after, before and after type analyses. You might notice something here that's kind of interesting. First of all, what DOT is very strong in promoting is this, that although we have a relatively small set here, this fatality number has gone away. And when you look statewide, there has not been a fatality in Wisconsin. Not completely true, but there has not been an operational-based fatality at a roundabout since one's been constructed at Wisconsin. There's been one fatality or two fatalities that have been either an intoxicated person who went through the center of the roundabout and somebody tried to jump the center of the roundabout on their motorcycle and was not successful. And you know, so we've had a couple of different types of what I call non-operational related issues. But for the most part, the operation aspects, we see that reduction in severity of crashes. But look at this number here, and this is just property damage only. And you can see it more specifically at a couple of locations. Meaning, so we see 40 here, 8 here. So that one's gone up significantly. And we also see 8 here, 32. So we had a couple of problem locations where we saw the significant increase in property damage only crashes. From a safety standpoint, we say, well, that's not necessarily a bad thing. You know, we can live with PDO crashes for the most part as long as people aren't getting hurt. But from Wisconsin DOT and perhaps Ed and others, I'm sure you've experienced the political pressure, right, of, you know, the legislators and some of the the anti-roundabout folks coming out and saying, well, I told you so. You know, look at how much those crashes are going up. And then that was additional fuel for the fire for the trucking industry, right, who are very much against roundabouts, trying to, especially the large trucks and the oversized, overweight community, that they do not like the construction of roundabouts. Okay, so well, we were able to deal with that a little bit and move forward in terms of, this is an empirical Bayes statistical analysis. Again, the numbers are more for reference purposes than anything I'm going to try and show you here. But this is, again, a very traditional way in today's world of evaluating safety issues, right? So big pile of spreadsheets, bunch of statistical analysis, using the latest and greatest methodology, which is Empirical Bayes, and identifying, you know, which locations had some sort of expected crash rate that was less than the actual crash rate. And when we saw that, they became pink or red in color here, and those were situations where we're seeing not necessarily a good situation in terms of safety. Something was going up. The Highway Safety Manual. Everybody experienced it so far? More ways than one. I see the laughs, right? So it's kind of become the latest and greatest, if you will, right, or the summation of all the safety data. And I know a number of universities around here have spent a fair amount of time looking and helping put this together. So I jumped from this roundabout analysis to this Highway Safety Manual by saying, you know, the key parts of this manual, predictive models, crash modification factors, again, the accumulation of all these common methodologies we've used for safety analysis is exactly what we did with the roundabout analysis. And we're able to get, again, I showed you some of the, at least in a quick way, some of the empirical Bayesian results. And using the same type of methodologies here, you know, we could come up with crash modification factors and find ways that if you do a roundabout like this in the future, here's what you should expect from a safety standpoint. The other common way of looking at safety-related issues today is using road safety audits. Anybody participated in a road safety audit in the past? So a couple of you. So for those who haven't, what it is, it's or defined, I guess, as a systematic method of checking the safety aspects of a roadway, of an intersection, whatever the issue it is. And it's a very formal, organized methodology. So, for example, if we were interested in the safety of an intersection, you know, perhaps we'd take Chris and Ed and Chris and a number of other experts out to the field, and we're all going to stand around the intersection, and we're going to watch it for a little bit, right, and kind of see if we can't figure out what some of the issues are from a operational or a design or a visibility or some of those core issues here. So when you combine the traditional approaches, when you use the Highway Safety Manual, when we implement issues related to road safety audits, would you all agree that it appears that we have a very good approach to analyzing safety-related problems? Is that fair? A lot of different methodologies we can use in order to help us understand where we have safety problems and where we need to make safety-related improvements. But have we forgot something? What do you think? Whenever somebody like me asks a question like that, I always tell my students, just answer yes, okay? And then I'll get to the point. All right? So, of course, right? We understand vehicles to some degree, and we understand the roadway systems, and that's kind of what I tried to set the stage for with the previous couple of discussions we've had thus far. And although I'm not going to talk about it, we can argue that vehicles themselves, in terms of the modern changes, the airbags, the crush zones, and all these types of things, have made some significant steps in improving the quality and the safety of vehicles. But how about all of us, right? These young drivers, those kind of drivers, right? These kind of drivers, right? And these kind of drivers. So we have this whole world of us that we could argue is somewhat incorporated into these traditional safety methodologies, but we can certainly argue that that's not the case in a lot of ways as well. So human factors become such a critical part of everything we do now in safety. And for those of you who aren't overly familiar with human factors, we have a long worded definition up there for you to take a look at. But I think we can simplify it by saying we're looking at how you and I as road users interact with whatever it is we're considering. The signals, the design, the operations. You know, pick your topic. Okay? And it blends into not only these inexperienced and these very experienced or older drivers that I showed you in some of the previous pictures, but it really blends into everybody. And that includes non-motorized users of the system as well, right? Everybody that uses our transportation system. So what we've done, like Oregon State has and a number of other state universities have, is implemented driving simulation into our transportation safety research. And I put together just a quick little video clip here to show you some of the elements of our simulator. So for those of you who are from Oregon State or been to Oregon State, the vehicle is essentially the same as theirs. We do a little bit different with the screens. So if you notice, there's a curvilinear screen in the front that extends 240 degrees. We have a rear view mirror and screen in the back here with a 5 projection system, so a few more projectors than what they have in Corvallis. But a very effective tool that helps us evaluate drivers in these safety analyses. It sits on a motion base, so although it's relatively subtle, you can see how the vehicle tips. So it's fixed base outside of the fact. We can get some acceleration and deceleration elements in it. And our student support help control the experiments, and although it's hard to see, there's a number of cameras embedded, so we can see people's feet and see where they're looking and see people's faces and evaluate how they're operating within some form of system. So when you put in a dynamic scenario there, you can see how it may look. So we believe, and I believe, and part of my message to you today is for us to really truly understand safety and how we can improve safety, we need to include a human factors component, and we believe things like the driving simulator are an excellent way to do that. In addition, we can also track eye movements. Pretty common for those who have simulators to include this particular feature, but either through a glasses type application like this or a dashboard type application, not only do we know how you're operating in some sort of environment, but we will also look and see how people are searching for information. So when it gets to signalized intersections and other forms of information within the traffic system, we can see how people are looking and if there's important places that information should be provided as people search for different types of decisions. Now, in the perfect world of driving simulation, all our scenarios would look like these wonderful video games that exist. Right? Anybody? This slide was provided to me by one of my graduate students, and I will admit I never heard of this, nor have I ever played it. But he tells me it's very fun and the quality of the graphics is outstanding. Right? So why is that? Well, the video gaming world is a multi-billion-dollar world now, right? So that's investing millions and millions of dollars in terms of improving the quality of the graphics and other elements of the software. Well, in our driving simulator world, we're not quite so lucky. We've been given some very basic applications of intersections and other approaches, and through either commonly used elements, Autodesk, MicroStation, and some of the wonderful things that are online in open source and free type applications, we're able to create some very realistic type environments and add 3D. So this is just an example build out of a divided highway system that we're working on to show you how, in a very crude form, we can get the contours and the slopes and that type of thing in the system and create, so this is a bridge that went into this connection. So you can begin to create some excellent, very realistic looking environments to help in the overall analysis of whatever it is that you're trying to look at. So in the remainder of my discussion, I want to show you some ways of how driving simulation can help us in safety-related topics. So let's talk about some traffic control devices here a little bit, and then I'll talk real briefly about some of these others here as we go along. For those of you who know me, know I would not be myself if I didn't talk about flashing yellow arrows and protective permissive left turns in some way, shape, or form, and I am not going to let you down today. All right, so we're going to talk about this for just a couple of minutes. But Chris and I, we began our professional lives to some degree in my academic life thinking about protective permissive left turns and how best to present that information to drivers. And for those of you who may not be overly familiar with this type of traffic control, I summarize it by simply saying that protective permissive left turns is a situation where we have an exclusive phase for left turns, meaning a green arrow, right? And then a permissive phase within that same signal cycle. And it became popular a number of years ago as capacity and congestion issues became more of a problem. So finding ways to process more vehicles per cycle and providing these two left turn opportunities became a commonly used methodology to help us with that. So what was the problem? Well, the problem was back to human factors. When we are going to make a protected left, what do we see? Green arrow, right? It's pretty simple. When we're going to make a permissive left, what do we see? Circular green, right? When we're going to go straight through a signalized intersection, what do we see? Circular green, right? So we had what seems to be perhaps even trivial or something that is hard to understand, but the simple fact that the circular green meant two different things. One if you're going straight, one if you're making a permissive left, it was problematic. It started to create safety problems. So creative traffic engineers around the country said, well, we're not going to wait for a solution. We're going to try and solve it ourselves. And along came the flashing red arrow in Delaware, and the circular flashing red in Michigan, and the circular flashing yellow in Washington, and the flashing yellow arrow in Maryland, and on and on and on. Okay? So we saw different combinations in different locations of the country where doing the right thing, right? They're trying to solve a potential or something they were experiencing in terms of a traffic safety problem. But the issue obviously is back to safety and traffic control devices and uniformity. What the Federal Highway Administration said at the beginning of this project was, you know, we need to put our hands around all these and try and filter out the ones that aren't working so well. And if we're going to do something different than the circular green, we need to identify which one that is and see if we can implement that nationally. So I and Chris and a number of other folks, we spread across the country looking at signalized intersections. And these are photographs, and I'm not smart enough to make them dynamic, so I suppose I could probably make a little flash thing there, but you're going to have to use your imagination that these signals are flashing in these various photographs. And we went out and looked at them, we studied them, and we did safety analysis, operational analysis, everything we could get our mind around in terms of understanding how these permissive left turns were operating. But what you also see, and one of the challenges we had was they were still confusing. And they were confusing, and you know, one of the key things, and although you can't read that, one of the key things, at least in my mind, is if drivers aren't understanding a system, you can tell that by the number of supplemental signs that are there to help explain what they're supposed to do. And what this sign says is something to the tune of, you know, yield on flashing yellow arrow and a number of other things. It's very wordy. But one of the first issues that we took a look at. Moving along, all right, so this is what Detroit was using in their flashing red. So they were a little bit sharper and put left on the top so to help us understand what signal head they were wanting us to look at. So in this region of the world, some of you may be familiar with the flashing yellows up in Seattle, so we looked at those very carefully. Dallas has a number, and Texas has a number of different things that compounded this that are a little bit beyond our discussion today. But something that they called the Dallas display and Dallas phasing were issues that went along with this protective permissive left turn application. So we looked at this type of signal display. This is out in Dover, so they had the T-type indication. And again, with all due respect to my friends from Delaware, when you need 1, 2, 3, 4, maybe 5 supplemental signs to explain what you want the drivers to do, you may want to go back to the office and think about that a little bit. But nevertheless, that's what they had. What I'm showing you beyond just my vacation pictures here is notice the different displays. Every location had a different display, which was what? Which was trying to say the same thing to all of you. If you were the driver there, all it was trying to tell you is that this is a permissive movement in addition to whatever you're seeing either protected or in terms of the adjacent through movement. One more shot, so more of the traditional methodology. So many of the locations use what we call the 5-section cluster, 5-section doghouse. And although this, although this picture is getting a little bit dated, you can see even with that, we're using supplemental signs. This is left turn on circular green must yield, and this one's a little dated. It's 1998, and back in the good old days, you used to get a gallon of gas for $1, right? So life was good way back in the 90s. But nevertheless, so this was a perfect scenario to bring back and combine this human factors aspects, driving simulation, with the basic traditional methods of safety. So we got the simulators that existed at the time around the country together, and we did this. We found 464 willing participants to come in and drive different types of signalized intersection scenarios. Protected permissive left turns, looking at all the different flashing combinations. And again, a very common use experimental design, looked at a number of different scenarios, found the widest range of people we could get to come in and participate. Notice, even though we focus on younger drivers, when you get into minors in this type of experimentation, there's a whole nother level of detail that comes into play in getting approval and that type of thing. So we chose to stick in the so-called adults range here, but some of the younger driver elements still highlighted themselves as the data began to come in. And many different scenarios. All right, so again, kind of a traditional approach, 14 intersections, number of modules, try to add the randomness and the variability to what people saw. And we came up with this giant, right, Chris? This giant database of information that we had to process. But at the end of the day, this is what we learned. We learned that protected permissive left turns are well understood, significantly reduced left turn confusion, no supplemental signs are needed, et cetera, et cetera. So what we see today is the implementation of the flashing yellow arrow. Some of you probably have experienced it now. I know it's at least creeping into Portland. I know it's been used in lots of other places around the area here in the state, but it's added to the MUTCD. Okay? So it's a good example, and perhaps in terms of the number of subjects, the largest example of using a combination of traditional methods and behavioral methods to implement a new type of technique. So that's it. I'm going to go through this a little bit quick because I want to get to a couple other things. I know my time is starting to get a bit limited, but it had a number of other benefits that we can talk more about if you like. But for those of you who are familiar with something called the yellow trap, the flashing yellow arrow minimized this condition that existed, and through a continuous application of the flashing yellow arrow, we could keep it on, and it doesn't conflict with that existing through movement. And because of that, we can continue through those phases and eliminate, in many situations, that common safety-related issue. So it had a number of other benefits that came along with it. For those of you who like good bedtime reading, the reports are still available. And there's a number of them that exist now, and there's been a number of follow-up pieces of literature that have gone with it as well. And I know there's some work being done in this area as well as we speak. So a lot of good information coming along. What I also have enjoyed, and maybe my audio is not here, and it's probably okay because I do want to move along, but this is actually a video that was created at the Illinois Department of Transportation. And if you do a web search, you'll see that many state DOTs now have created some sort of informational video and put it online on how to operate under these type of conditions. So to some degree, I guess we consider that flattering, that people have actually bought into some of the results of research, which is nice from our perspective. But it's being used quite regularly, and I think for the most part, people are understanding that as a good safety improvement. All right, so my last couple of minutes, let me quickly just go through some other ideas here for you on how we can incorporate different types of safety analyses. We talked about road safety audits briefly just a second ago, and the other thing, or one thing that we're doing to try and add to that is something that I call a virtual road safety audit, where we bring in the driving simulator. So back to basic road safety audits, it's a formal examination, as we talked about, independent process, skilled examiner, restricted to road safety issues most often. But we can get out and look at it. But we can also combine it with a dynamic aspect. So let me show you one thing that we're doing to do that. This is the Marquette Interchange. It's in Milwaukee, the most active interchange in the state of Wisconsin. And there's a loop there, a loop road that goes from eastbound to northbound, a very tight curve. And when you see articles like this in the paper that says 39 crashes in one spot of the Marquette Interchange prompts changes, well, DOTs don't like that type of publication, do they? And we won't read through all that, but the bottom line is we're having a significant safety problem here, and some things were added, so added a warning sign and those type of aspects. But we still continue to see things like this. So kind of watch up at the top of the screen, and people hit the curve a little bit hot, coming down through there. Like this guy, off they go, kaboom, right? So we're seeing lots and lots of those types of crashes. So people were taking the curve too fast. Well, there was a number of things that have been done to kind of jump to the point, so some warning signs, some dynamic signs. But this is something that we're actually looking at now in more detail by driving. So we actually went out and drove this with a LiDAR-based type vehicle, and we've created a 3D model of this curve that we can drive in the sim to see if there's some other behavioral or other aspects of the curve that we're missing that help us identify what the best safety problems are. So this is not the curve. This is State Street, Madison, but you can see here that we can take a visual world like this, and although we removed all the trees, we can create a 3D environment that's drivable within the simulator. So we can take any type of environment and replicate it and allow us to analyze it in a formal way. So that's the actual picture. That's the simulated picture, so you can see the quality of the graphics have significantly improved. Okay? So there's lots of different things we can do with this type of design. So real briefly, I'll just touch on a couple of other areas. Design itself. When I first got into this, I used driving simulators when I was at the University of Massachusetts. So you all know about the Big Dig, right? So we took the elevator freeway and put it underground, made a nice urban landscape there in the city. But although those picture quality is not the best, that's inside the tunnel. Well, a lot of what you see inside the tunnel today was a result of driving simulator studies prior to its construction. And that's mostly related to traffic control devices, but in a very limited tunnel height of 14 or 14 and a half feet, whatever it is, you know, getting guide signs and other pieces of information to the driver was quite challenging, especially if you found yourself behind a large truck here and your vision was limited. So it's another simple but very important example of how these simulators can be used. And now, not necessarily a tunnel-based design, but this is the next major interchange in Wisconsin that we're going to be reconstructing. We have began to simulate this entire intersection, or interchange, I should say, so it can be driven in a design standpoint. We can make the appropriate changes before construction. There's a whole nother world that we could look at in terms of driving simulator use to things inside the vehicle, and this whole world of driver distraction. And I'll simply say that we're doing a lot of in-vehicle type analyses, and although it's kind of difficult to see, the center dash of the vehicle and the dashboard are programmable and dynamic, so we can add lots of different features and see how drivers react under different conditions and scenarios. But at the end of the day, we still have that challenge, right? We have that challenge of combining what I'll call again, traditional traffic safety engineering and methodologies. And what I've tried to introduce to you here a little bit at the end, some of the human factors engineering, and what I'm hoping you have had a chance to see that, at least we believe, adding driving simulation and these types of techniques to the overall evaluation of safety is a necessary step if we're truly going to understand how to make significant safety improvements in the future. Okay? So the future of traffic safety research must move beyond what I've called these traditional methodologies, in my opinion. And that change includes these advances in bringing the driver and the road user into the environment and part of our overall analysis process. Okay. Questions? Hopefully I've stimulated some thought and or things that you may or may not agree with. I'm more than willing to listen to anything you have to say. Yes?
Hi, thanks. I was wondering in the simulator if, with the eye detection or the eye movement detection, if there was anything surprising or just unexpected that came up that would suggest the need for changes to what is understood as the traditional driving experience.
Yeah. Great question. A couple of quick responses to that. First of all, eye tracking in a vehicle from an experimental standpoint is extremely difficult. And it's difficult because the calibration, the mechanics, and the details of some of these systems are a little bit hard to use. But having said that, back to your question, one of the things that we noticed, and it really trickles back all the way to the protective permissive left turn research, is signalized intersections and how drivers search for information. And what we found was in some initial analyses is that when drivers didn't understand the information that was presented to them as part of the traffic signal control, they didn't look at it. So we saw a quick glance back and then no more consideration of the display. So in permissive movements, what they focused on is that opposing traffic, right? So didn't know if they could go or not, and you saw how they were, the lack of the, well, let me rephrase it a different way. So you saw the people that understood are more of the traditional driving environments with protected, and the search and the scan and the fixation was all on the signals, waiting for the opportunity to go. When you saw and correlated that data with people who said they did not understand the system, it went totally away from the traffic control. So that was one interesting finding and something that we continue to look at and build upon, because I think that's very important in terms of how we place some of these new technologies, new ITS technologies, and some of these creative traffic control things that we're implementing now. I took a tour with the City of Portland's traffic engineer here this morning, and he showed me a number of the neat things that are being implemented. And they're nice, but it adds a whole new world of visual analysis that one needs to do with the dynamic LED signs and things. And drivers that don't understand it may not necessarily search up there.
The question is kind of two-part, and with the traditional method of gathering data and numbers, is there a factor or column in there that considers whether it's a routine intersection for the person that's had that accident, or whether they're like through traffic, like out of state? And then is that able to do something also in the simulator, send somebody through the same intersection 100 times, yep, and see if they start not watching the signal?
Yep. Great question. The answer is yes and yes. Right, so the and the traffic analysis. So let's relate it to the median crossover stuff and the roundabout stuff that I showed you. Very much an important variable is looking at where these drivers are from, especially in median crossover. You're probably not really familiar with Wisconsin, but let me generalize by saying on weekends, especially in the summertime, the city of Chicago empties out and it all goes to northern Wisconsin. It's very much of a touristy, North Woods, kind of in a region similar like it is around here. They like the hiking and camping and fishing and that type of thing. So we got this tremendous flux of vehicles on Friday, northbound, and the same thing southbound. So one of our theories was these mini crossover crashes primarily these out-of-state drivers, and because they're 3 or 4 hours fatigued by the time they get to these locations, and et cetera. Some of that was observed, so that was a fair component, but we always, at least in the research I'm involved in, we always try to see if we can identify the attributes of the driver beyond just male or female, but where they're from and where the beginning of their driving experience started. And then we can also do that in the simulator as well. One more quick response to your question. The reason we bought the simulator that we have, it's identical to the one at Oregon State. It's identical to a couple of others that exist around the country, and we can link them all together. So one of the things that we can do now that overcomes some of these different drivers in different regions, different locations type thing, is we can run exactly the same experiment, present the exact same vision to the driver, but we can have Oregon drivers, Wisconsin drivers, Mississippi drivers, Massachusetts drivers, Texas drivers. So there's a number of them that we can link together now. Go ahead.
Did you discover, I guess when you were graphing this out, if there was some sort of balance point between providing the driver with too much information and then providing them with none at all? I'd make, I guess, the arguing point that having some information as somewhat of a constant variable keeps drivers from becoming complacent, or when they enter an urban area, not understanding the context of what's going on versus what they were used to for several hours driving through a rural situation.
Yeah, absolutely no question, right? That we can overwhelm drivers with too much information, and I can show you many examples of that. And frankly, I think there's, so some of the neat things that are going on in the city here are borderlining on providing a little bit too much dynamic elements to that situation. So, yeah, I think we have to take that into account. We can look at that. Keeping it simple is always the best methodology and uniform, right? So I guess I'm missing the last part of your question, perhaps, but I'm agreeing with you that the simplest and more straightforward that we can operate a system, we tend to see the best operation, the best safety performance.
So having lived in Wisconsin for a while, a couple things that I remember about it is that it's dark and cold and icy and snowy. And so
You need to come in July.
I mean, no, I lived there too, but the winters were very long, and was wondering about how you incorporated weather into these, especially with roundabouts, the constant turning on ice is never fun, and wondering how that's incorporated, and also kind of sliding across medians.
Well, I'll answer your question in a couple of different ways. All right. So first of all, you live there, so you've experienced some of it. But the icy days aren't as bad as what we may all think this big upper north Midwest type thing is. But yes, there's no question we get colder temperatures and icy conditions. The median crossover, there's definitely an attribute there that has to do with slippery, icy, snowy roads. So there is a little peak in those types of crashes when those things have happened. There was not a weather. Getting back to the statistics, not a weather variable that seemed to be significant to the roundabouts, and the logical answer to that is just because of the slower and lower speeds, right? And some of those attributes that go along with it.
And then I guess as a follow-up, are the simulators, can you make icy and snowy conditions with the simulators?
Absolutely, right? So we can change all the feedback variables. So, so just like if you turn the wheel and your car continues to go straight on an icy road, we can make all those types of things happen. So, in fact, the little dynamic example I gave you towards the end of that video was a raining condition. So it doesn't quite rain as much in Wisconsin as it does here, but we can also simulate any one of those type of conditions as well. But your core point is absolutely weather is significant in all these types of analyses, and yes, different parts of the country are going to experience it differently. Yes.
Is there any evidence to suggest that driving on the other side of the road, i.e. having the oncoming traffic on the right instead of the left, could this be safer?
Well, I can tell by your accent where you're coming from on that question. So, I don't know if you're thinking about the roundabout specifically, or if you're thinking about just all the things in general. No, at least in my experience, and we've actually experienced a number of international related research activities and using Australian-based software, which is similar to what you're thinking about. But no, I'm not aware of anything that's correlated between the British and Australian and other methodologies of driving on the left, I guess, versus the right. But I guess it depends on where you're from and where you live. You probably always think the other way is a little bit better, maybe, huh? So that transition is always hard.
I'm curious if there's any evidence that shows that driving behavior becomes more risky as we make these vehicle safety improvements and a lot of these traffic operation improvements, like the medians you talked about at the beginning of the...
Yeah, I think the answer to your question is absolutely yes. And you see it just in terms of general driving behavior, right? So where I correlate my response to questions like that is just think about headways and gaps and congested driving. And what we see, for example, if you're familiar with the term saturation flow and saturation flow rate, that even as speeds change, the gapping between vehicles is not really changing, even at the upper speeds. So we're able to some degree, from a good sense, operationally, we can jam more people together at higher speeds and move more vehicles per hour. But from a negative sense, we have all these safety/human factors related variables that come into play. So why are people willing to accept these smaller gaps and a little bit more risky behavior and selecting smaller gaps when you lane change and things? And I think a lot of it has to do with the safety that you feel in your vehicle. That also goes into the speeding issue, right? So why does everybody speed? Everybody speed? Right? Do we all speed? Well, there's a design-related issue we could argue, right? So our environment makes you feel comfortable going faster, perhaps in the posted speed. But you see in conditions that are either constricted or in construction zones, wherever you may want to pick, that when things aren't as open and free feeling as others, then that reduces your speed, right? You drive slower when you don't have that comfort factor. So there's no question that how drivers operate, at least in my opinion, within the system today is in part due to willing to take more risk because of the safety they feel within their vehicle.
We have some questions from the web. I'll get to maybe just at least one of them. Is there any interest in including qualitative research, such as driver interviews, in safety analysis?
Absolutely. So everything that is driving simulator based also includes a qualitative element. And in fact, some of the output of driving simulator based research is essentially that. We're watching, you're observing what drivers do under those various types of conditions and making an assessment like we did with some of the flashing yellow arrow research on, did they do something right or do something wrong? And in the assessment of doing something wrong, it was very important to us what they did wrong. And that was the key part of the flashing yellow arrow, is if they didn't understand what it meant, drivers tended to stop and yield and try and figure it out. Well, not necessarily ideal operationally, but it's ideal from a safety standpoint. That's indeed what we wanted them to do, right? So there's every part of a human-based, driving simulator-based research component will include some sort of qualitative analysis.
Can I do one quick follow-up, another web one? Are the driving simulators adaptable to commercial vehicles, like
Yes.
large trucks?
Yep, they very much are so. We have a large commercial trucking company in Wisconsin that's called Snyder. So maybe you've seen them. They're always orange in terms of their trucks. They're very much a large national firm. And they have a truck driving simulator that we partner with from time to time. So they, same type of situation, just a truck cab instead of a vehicle. So we're able to see how truck drivers can better improve performance under those types of things as well. And it's gone beyond that. I mean, for those of you who are familiar with the Oregon State system, they have a bike simulator, connected to theirs, and it's fascinating. When I looked at it yesterday, I thought it was really, really exciting, the number of things that you can do by getting the so-called non-motorized aspect into the driving simulator environment as well. We also have a motorcycle simulator that we work with in Wisconsin, so there's really all modes now have some form of simulation that's possible.
Follow up to the truck simulator. Did the data show more crashes with trucks in the roundabouts?
No, the data in terms of our roundabout analysis did not see trucks being any more problematic than other types of vehicles, and most of the crash reports were automobile type applications. But I think we can safely say, and if you talk to truck drivers, maneuvering through roundabouts is extremely difficult. Most truck drivers, if they have the opportunity, will take routes that avoid roundabouts, especially if they have a longer load. And then, as I'm sure Ed's familiar with, from a political standpoint, and lobbying and making sure we don't get these types of things. We've had a lot of kickback from the trucking industry. And again, as I mentioned, those who are involved with specialized transportation and some of the larger loads, they're very much opposed to roundabouts simply because of the difficulty of maneuverability.
I have a question. With the roundabouts and the safety, did you see any change in the pedestrian safety analysis? I've been in both, and it felt a little less safe when there isn't a white man, that I can look at and let me know I can go.
Yeah, there is a whole nother world of discussion that we could open up here if we wanted to talk about pedestrian-related issues at roundabouts. We didn't. I do not believe there was any pedestrian-related crashes in our database that we considered in our analysis. But obviously, accommodating pedestrians at roundabouts without the stop-and-go traffic becomes much more significant. We're not using any of the pedestrian don't walk signalization. Those in the visually impaired community are very much opposed to roundabouts from that standpoint, where it's difficult for someone who has a visual handicap to traverse a roundabout without the audio cues that they're normally used to in making that type of crossing. So so there's a whole world. We've actually, as a bit of a sidebar, we've actually looked at some research in our lab that looks at some combination of signalized intersections, meaning like hawk signals, if you're familiar with those, or hybrid pedestrian beacons that provide that. And if we move them back a little bit from the roundabout, there's some ways to still keep the roundabout efficient and get pedestrians across. But the argument to that, of course, is, well, if we're going to build a roundabout, then why do we go back and then signalize all the approaches? Why don't we stay with a signalized intersection to begin with? So there's a lot of trade-offs there.
I think we're at our time limit, so before we thank Professor Noyce for his great presentation today, there's no class next Friday. PSU's closed for Thanksgiving, so the following Friday, Roger Chen, he's a postdoc here at Portland State, is going to talk about identifying market segments based on observed travel and activity patterns. So with that, let's thank Professor Noyce. Thank you.
Thank you.